Okay, thank you very much. My name is Naohisa Kanda from NUS, which is a consulting company in Tokyo. I have been attending ISA meetings several times, and this time I am here on behalf of Jogmek, one of the ISA contractors. First of all, we would like to thank ISA very much for giving us this opportunity to present one of the results from Japan's experience obtained from the pilot study conducted for the polymetallic sulfides in Okinawa, Japan. Although there are several different research objectives and results from the pilot study, today I will present you the result of the impact prediction study using a numerical mathematical model and its verification for the environment impact assessment of PMS. The whole project was led by Jogmek, and the study presented here was led by SAT. Our company, Janus, was mainly involved in the model development. To tell the truth, I wasn't directly involved in this study, and I'm not model expert, but I am presenting on behalf of Jogme and SAT today. So if you have any questions about this presentation, I appreciate you will contact me later with your questions, and then I will pass your question to the appropriate people in the project. This slide shows the timeline of the project in terms of study activities in the field of environment impact assessment. As we probably know, it was 2017 when the Minister of Economy, Trade and Industry of Japan and JOGMEC conducted and succeeded first pilot test of excavating and or lifting for seafloor PMS, lying about 1,600 meters below sea level near Okinawa Prefecture. The project actually had begun since 2008, and the environmental study also started at the same year. The Eia project consists of the three parts as shown in this figure. First, baseline survey followed by monitoring survey for the environment data. Second, prediction model development to assess the impact of mining activity. And third, discussion of conservation measures, including some biological and genetic analysis. JOGMEC has been examined and reviewed how to conduct the EIA for the PMS mining. As shown this figure, JOGMEC had identified the activities that would have impact during the mining operation, which is blue column, and environment issues arising from the impacts of such activities, which is green column, and then proceeded to develop several different types of prediction models to assess the extent and the level of each of these impacts, which is yellow column. This presentation will show you the result of the seafloor disturbance experiments conducted in 2017. We predicted diffusion process and resedimentation level of the plume generated from the disturbance experiment using the prediction model, and we examined the accuracy of the model by comparing the predicted result to the data observed from the monitoring survey at the site. The experiment was conducted to quantitatively evaluate the environment impact of mining. The experiment process is as follows. By the rule for the evaluation, first we developed and used a mathematical model for simulation to predict the extent and degree of impact on the environment. Second, we determined survey starting point based on the predicted result and finalize the plan of experiment. Third, we conducted environment survey before the disturbance experiments to collect the baseline data. Fourth, we conducted the disturbance experiments and environment monitoring survey during the experiment. Finally, we observed the environment data after the experiment to evaluate the model performance. In reality, however, we did simulation again after the disturbance experiment to verify the model, which means the process between fourth and fifth. This is because the survey starting point was slightly moved from where we planned, and the time when we started the experiment was also changed from the initial plan. This means that we compared the observed data from the experiment to the predicted data simulated after the experiment, but not before the experiment. The disturbance experiment was conducted in January 12, 2017, at the inactive vent area of the sea hole reside in Okinawa Sea area, which is southeast of Japan. The size of the hole was 6 kilometers long and 3 kilometers wide, with the deepest water depth of 1,665 meters. The experiment was conducted using this type of the load header as shown in the picture, which we called SUR. SUR was a small in size and was developed specifically for the drilling experiment during the pilot study. Monitoring survey was also conducted based on the categories listed in this table during the experiment and half year, 1 year, 2 years, and 3 years after the experiment. Furthermore, in regard to the midwater ecosystem, the effect of the noise to tuna was monitored. This slide shows the re-sedimentation data observed from the monitoring survey after the experiment. We measured the thickness of re-sedimentation at the 9 site from NM1 to NM9 that you can see in the map, the block dot. The right-hand bottom picture shows the sediment trap we used to measure re-sedimentation thickness. Then, as you can see from the table, among the 9 sites, resedimentation of the sediment was observed at the 5 sites, NM1, 4, 5, 7, and 9, with the largest amount at NM7, which was southeast of the disturbance point. We were able to determine resedimentation from not only the increased thickness and the change of the particle compositions. At the NM7, monitoring survey found that the abundance of Harpocticoida, which is a species of copepods, meiobenthos, was decreased, most likely due to the resedimentation. Therefore, we kept conducting monitoring survey regularly since then to observe the effect of the impact to the ecosystem. This slide shows the simulation conditions of the prediction model to estimate resedimentation process. For this simulation, most of the data used for the model parameters in the table were collected at the disturbance point. The amount of turbidity generated by the disturbance experiment was set from not only mining activity, but also resuspension of sediment arising from the landing movement of the road header. Flow condition at the area at the time of the experiment was estimated using the data obtained from the past ADCP, acoustic Doppler current profiler, as shown in this bottom figure. This bottom figure shows the flow condition, speed and direction from January 11 to 12, the day before the experiment to the day of the experiment. You can see the flows are quite different. This slide shows the result of both simulation and the monitoring survey. A comparison of the two results show that the simulation results were in good agreement. with the distribution pattern and resedimentation thickness from the monitoring results. The highest thickness was observed at NM7 and along the southeast slope from both pictures. This indicated that our prediction model very well predicted the behavior of prunes. However, it is also important to notify that although the detailed data is not shown here, when we looked into the predicted data at the final spatial scale, like a 5-meter square mesh, we found that the level of the resedimentation thickness was underestimated at some sites. This means, on the one hand, this suggests that the model may need further modification, further improvement. On the other hand, actually, we are not sure if such a fine-scale accuracy is required for the EIA in the deep seabed mining. We think that this is a future issue to be addressed. As I explained earlier, our initial plan was to conduct simulation before the experiment to evaluate the model. We wanted to start the experiment as we simulated, but in reality, we couldn't make it. We were not able to start the experiment at the starting point we simulated. This slide better reflects why I brought this issue. This slide shows the result of the two simulations, before and after the experiment. We had to conduct the simulation after the experiment because the disturbance starting point slightly moved from where we planned, and the start of the experiment delayed too. Then we got quite different results from these two simulations, as you can see from these left-hand bottom figures. As you can see from the top pictures, the disturbance point moved only 10 meters, and the experiment started just 1 day later. However, because of this, some parameters, such as the current flows patterns, also differed, as is shown in left-hand left-hand picture. So these two simulations indicated that the impact of the mining to the environment could be quite different, depending on where and when we start the mining operation and its duration. This is very important finding when we develop conservation measures. This slide shows a summary of the simulation results for the disturbance experiment. The numerical mathematical prediction model will be a great tool to simulate the dynamics of the operational plume and predict the impact of the mining operation, because the estimated pattern of the resedimentation thickness and the plume distribution range were agreed with the monitoring result. This also suggests that backward calculation using the model may be able to provide information for the delineation of the buffer zones. In addition to that, as raised during the Ebola workshop, we showed that the location of the mining with respect to currents and topography, as well as drilling conditions, also influence the dispersal of the plume. So simulations to predict the impact of the mining should reflect the mining activity as precise as possible, and multiple times of the simulation will probably be necessary. Some future tasks are: we need to examine the applicability of our prediction model to other areas. We keep looking for other prediction models to further improve simulation accuracy. As we found the decrease of some of the Mayobenthos species, development of the ecosystem model will be useful, which is we are trying now. Relating to that, we are also discussing how often and how long we should monitor the environment. Thank you very much.